Hi, and welcome to this tutorial at RecSys 2020 on adversarial learning for recommendation, applications for security, and generative tasks, concept to code. So here you see the speakers of this tutorial, and we will have Walter, Yashar, Felice, and me. So we are all from Polytechnic University of Bari in Italy, and we work together at the Information Systems Laboratory. So if you are interested in adversarial machine learning for recommender systems, so you may take a look at our survey, which is publicly available on Archive, or if you want to wait a bit more, there will be a book chapter on the upcoming third edition of the Recommender Systems Handbook on the topic. It is very interesting to us to keep everything updated on our website, on our repository. So we have this GitHub repository where you can find all the approaches related to adversarial machine learning for recommender systems and the generative adversarial networks for recommender systems. In this repository, we save everything, all the approaches that are published in the literature, and whenever possible, we also make the code available. So this is the plan for today. We have this tutorial divided in mainly three parts. So we have the first part, which is an introductory part, and I will present this part. This is about basically the foundations of adversarial machine learning and generative adversarial networks and the way they are connected to each other. Then there will be a second part related to adversarial machine learning for security in recommender systems. And here we will see how to put together recommender systems and adversarial machine learning and how adversarial machine learning may affect somehow the field of recommender systems. And then we will see some attack and defense strategies in recommender systems based on adversarial learning. The third part is devoted to GAN, to generative adversarial networks, and mainly to GAN-based approaches to recommendation. So we will see many applications as well as many different algorithms and approaches based on GAN for recommendation. Part 2 and part 3 come together with a hands-on session where you will play with the code that we will make available about adversarial machine learning, so attack and defense strategies, and on GAN-based recommendation. So what is the focus of this tutorial? Well, the main focus of this tutorial is adversarial learning for recommender systems security mainly. So this is something which is at the intersection among machine learning, recommender systems, and information security. So by looking at these three fields together, we will talk about on how these fields, they talk to each other, and we will talk about adversarial learning for recommender system security. But what we will see is that many principles that are behind this adversarial learning for recommender system security are somehow useful, and they are actually used to create this new breed, this new family of recommendation approach, which are based on generative adversarial networks. So we will have on one side adversarial learning for recommender systems, so we will have attack and defense strategies, and on the other side, we will have generative adversarial networks for recommender systems. These two fields, they do not share just the word adversarial, but we will see that they share some principles, so that's why they are put together within this tutorial. Adversarial learning for recommender system is getting quite famous within the field. So that's why we have seen that in the last 3 years we have collected more than 80 papers in the main conference and top journals in the field. So this is a clear sign that this is a topic that is getting hotter and hotter. So that's why it's interesting to know something about it. And the same is for the approaches that are described within this paper. So we see that initially, starting in 2017, basically, we had some approaches to recommendation based on generative adversarial networks, based on GANs. But what happened in 2018 is that also some approaches or some papers on adversarial machine learning started to be published, and this is an increasing trend. So we see that in 2020 we have basically this trend which is increasing. Well, actually, the data here is not complete, but we see that the interesting is still there for this topic. So we put together recommender systems and adversarial learning. So let's see what happens when we put together these two words and which are the elements that are interesting related to these two different words. So we know that for recommender systems, we have on one side, we are interested in evaluation goals, which are, for example, accuracy and everything that is named beyond accuracy evaluation. So, for example, we have novelty, we have diversity, we have coverage, and so on and so forth. But what we are seeing is that also security, privacy, fairness, and scalability, they are gaining momentum. And in particular, as for the security part, this is where adversarial machine learning is focusing. So this is where adversarial machine learning plays a role. On the other side of the slide, we see that we know that there are many recommendation models right now. So we have, for example, collaborative filtering, content-based filtering, context-aware hybrid approaches. But specifically, we see that within these recommendation models, adversarial machine learning and GAN-based approaches are mainly available when we talk about model-based, graph-based, and deep learning-based approaches. So, but this is what happens when we put adversarial machine learning and GAN within what is already there. But thanks to this new approaches, thanks to these new topics within the field, we see that there is something new that is increasing, and this is the ability of learning in adversarial settings. So, what's the meaning of creating a robust algorithm that is able to somehow react in a way to adversarial attacks? These are the main goals of our tutorial today. So basically, we want to bridge the gap between these two fields of recommender systems and security. And during the tutorial, you will hopefully understand the key concepts in adversarial machine learning, and you will understand what is adversarial machine learning and what is generative adversarial machine learning. We wanted to state this clearly because when we started work and to read the papers in the literature, we, at least to our understanding, there was a bit of confusion between adversarial machine learning and generative adversarial network. So somehow, some papers talked about something referring to something else, and vice versa. So that's why we want to clearly state that these are two different topics and approaches, even though they share something. Another goal of the tutorial is to make you able to play with these approaches and to make you familiar with the code and the algorithms related to attack and defense strategies, as well as to GAN-based approaches. And finally, we are very happy to present the future direction in these fields that could be very useful for the next research lines. So let's start with some motivation. So basically, we see that if we look at Google Trends and we search for adversarial learning, we see that starting from 2016, there has been an increasing interest in the topic. So we started in 2016 with some interest in adversarial machine learning, but this is an increasing. There is an increasing trend in searching these terms. And also, if we look at the related topics to adversarial learning, we see that more or less there is everything we have somehow cited so far. So we see that we find generative adversarial networks. We see that we find adversarial machine learning, generative models, and deep learning, if we look at the related topics. But on the other side, if we look at the related queries, we see that we have deep learning, adversarial networks, generative adversarial networks, and GAN, which are which is the acronym for Generative Adversarial Network, as well as Adversarial Machine Learning. So more or less everything is here, is within this related stuff, and everything is within this tutorial. So we are very happy that everything is here. So when we talk about adversarial machine learning, this is the most famous example because everything started with a panda. So what happened here? In this experiment, it was shown that if we add some adversarial noise to a picture, who's classified as a panda by a classifier, then this picture plus the adversarial noise is no more classified as a panda by the same classifier, but now it is classified as a gibbon. Well, actually, if we as humans, if we look at the two images, the one on the left-hand side and the one on the right-hand side, we see that we cannot see any difference. So basically, there are two pictures of the same panda. But actually, after adding this adversarial noise, the classifier has been full. So there is something wrong somewhere. Well, actually, this is a serious problem also when we adopt our AI systems within the physical world. Here we see an example where by adding some darker and lighter and brighter sections and areas to this stop signal, it is no more classified as a stop signal, but it is classified as a speed limit. And this signal is classified as a speed limit, even though, irrespective of the distance of the signal, or the way it is oriented, and so on and so forth. So it is not the way we frame the signal, but there is a problem in the signal itself, the way it has been modified. And the same is with this other signal, where we see that there is a clear misclassification of the sign. So we have this turn right sign, which is classified as a stop sign. But how this affects the recommender systems scenario? Well, in this case, we can show you this example coming from a paper that we have published this year, where we attack the recommender system based on BPR, on visual personalized Bayesian ranking. And in this case, we see how by attacking the images coming together with the item, it is possible to somehow change the ranking in the final recommendation list. And this variation within the recommendation list, it is not a random variation, but it is an engineered one. So we wanted that a specific item had to be in the highest part of the ranking instead of being in the lowest one. So this is a way how we can attack, for example, a recommender system by using, in a straight way, some of the approaches that are coming from computer vision. But what is the origin of such failure? So there is clearly a failure here, but we want to find the origin of such failure. Well, a possible idea is that this failure lies where there is the decision boundary of the model. So we see that the decision boundary of the model is not exactly the decision boundary that we have within the data. So the model slightly differs from the true data distribution. So that's why we can somehow add some adversarial example just in this space that we have between the actual boundary and the boundary of the model. So the idea could be that of pushing this adversarial examples across this boundary such that they are misclassified. It seems that everything is about data. So if we look at this seminal paper published in 2014, so the authors here, they say something really really incredible. So they say that they found that adversarial examples are relatively robust and are shared by neural networks with varied number of layers, activation, or trained on different subsets of the same of the training data. So this means that if we use one neural net to generate a set of adversarial examples, we find that these examples are still statistically hard for another neural network, even when it was trained with different hyperparameters, or when it was trained on a different set of examples. So it seems that everything is within the data. So actually, we understand that everything is within the data distribution, and the probability distribution that we have within the data. But actually, even though data play a very important role in this field, actually there is this other very interesting paper saying that okay, data is very important, but we also have to consider that adversarial examples can be directly attributed to the presence of non-robust features. So these features are features that are highly predictive, yet brittle and incomprehensible to humans. So this is interesting because if we look at the final part of this slide, we see that this perspective established adversarial vulnerability as a human-centric phenomenon, since from the standard supervised learning point of view, non-robust features can be as important as robust ones. So in this case, we see that, well, adversarial learning is something about data, it's something about our algorithms, but humans play a role within the game. Okay, so let's start with some foundations about adversarial machine learning, and we start with this taxonomy of adversarial attacks. Well, when we talk about adversarial attacks, we can classify them within different dimensions. One of these dimensions is attacks timing. So we can attack a model at training time or at inference time. So at training time, we attack the model when we add new data. So we perform a data poisoning. This attack is made before the model is trained. So in this case, as we see in the picture on the right-hand side of the slide, what we are doing is to move somehow the boundary of our classifier. So if we look at this part of the image in the slide, so we see that we are moving the boundary, the original boundary of our classifier to a new poison boundary. And in this case, a point which was classified as red before now is classified as green. We can also attack the system at inference time. So we can also attack the system after it has been after the machine learning model has been trained, and so the attack occurs during the inference phase. This kind of attacks are also named evasion attacks, and in this case, what we do is to move the same. We leave the boundary as is, so we don't move the boundary, but we can move one point from one class to another one. So in this case, we are moving this point from the red class to the green one. Another dimension. So as when we talk about poisoning attack in application literature, so this is actually something that has been studied already in the past. So we have that one of the first interesting paper in this field has been published in 2012. And it is based on an attack against the SVM, support vector machines. But also in the recommender systems field, we know that poisoning attacks are nothing new, because we may know from the literature that there are many papers talking about the so-called shilling attacks in recommender systems. What is different in this case is that for shilling attacks, we mainly have hand-engineered poisoning. So Everything is not completely driven by an automated process or by a machine learning process. Going back to the taxonomy of our attack, another dimension is about the attacker's knowledge. So depending on the knowledge that the attacker has on the model, we can have a white box, gray box, and black box attacks. So as for white box attacks, we have that the attacker knows everything about the model. So he knows the training data, he knows the parameters, he knows the model, he may know the hyperparameters. So he has a complete access to everything about the model. So this is, in this case, the attacker is in the best position possible. On the opposite side, we have a black box attack where the attacker does not know anything about the model. So he doesn't know which kind of model is there. It doesn't know anything about parameters, hyperparameters, or even data. So what the attacker can do is just to probe the system and try to understand what is the model, what is the probability distribution of the data, and so on and so forth. So this is the hardest position for the attacker. And of course, we have something in the middle where the attacker may know something about the system. The final dimension for our adversarial attacks is about the goal of the attacker. So we can have two different kind of attacks. We can have targeted and untargeted attacks. In the first one, what we do is to force the classifier in make prediction into a target class label. So meaning that we attack the system such that points and data are misclassified, but at the same time, we are not satisfied by a misclassification per se, but what we want is that, okay, the point is misclassified, but it is classified in a target class that I decide. Differently from targeted attack, we have untargeted ones where the aim of the attacker is to fool the system and is not interested in the final class of the final classification class. So the attacker is only interested in making an incorrect classification. Okay, so let's try to introduce something more formally, just to give you to introduce the formalism that we will use during the slides and during this tutorial. So we all know that we have this supervised classification problem. We start with supervised classification problem where we have a loss function with some parameters omega, and we have some data x with the corresponding label y. So what we want to do is to find a value, the best value for omega, such that the loss function is minimized. What happens in an adversarial setting? Well, basically, we have more or less the same problem, but in this case, what we want to do is to add a perturbation to my data. So we want to add this delta adversarial to my perturbation such that I am maximizing this time the loss function. So I want to decrease the performance of the system, because I want the system misclassifies as many data as possible, or at least the points that I'm interested in. So that's why we introduce this perturbation, but at the same time, we want this perturbation to be as small as possible. So we don't want to be, we don't want this perturbation to be perceptible immediately. So we want this perturbation to be very simple. So that's why we add this constraint, and we say that the norm of my perturbation must be equal or lesser than an epsilon, where this epsilon is the so-called perturbation budget. So all the algorithms that work to find such adversarial perturbation, they are named adversarial attacks. So this could be a possible framework So, for example, if we look at the image on the left-hand side, so we see that this image is clearly an image represented a 1 as a number, and it is classified as 1. So what we want to do is to add some perturbation to this image such that it is no more classified as 1, but it is classified as 4, for example. So what we do is to look at the model, to look at the features that somehow are more important and plays an important role in the classification of the image. And based on this analysis, we add the perturbation. And once we add this perturbation delta x, so once we have this perturbation added, so we check if the sample plus the perturbation is still classified in this case as 1 or 4, so it is misclassified or not. If this is the case, then we are done. Otherwise, we iteratively go back to point 1, and by looking again at the features that influence the final result, we modify the perturbation. As for the attack methods, most of them have been mainly proposed within the computer vision domain. So the first one can be the LBFGS, where the authors use limited memory BFGS to perform an attack to a neural network. And very interestingly, this attack solves the problem with linear memory requirements. Then in 2015, we had this paper by Goodfellow and other co-authors, where they proposed this FSGM, this fast gradient sign method. And in this approach, they work on the gradient of the loss function to work on the constraint problem that we have seen before. After this paper in 2017, we have this Carlini-Wagner approach where they refine the LBFGS attack to defeat defensive distillation. Defensive distillation is a defense strategy that we'll see that we will see in a while. And then after other approaches have been proposed, such as the JSMA, the deep field approach, and other are coming. So what is the intuition behind FGSM? Just to give you an idea of how these methods work. So we have our perturbed sample, we have X prime, which is equal to x0 plus our delta adversarial, which is our perturbation. So if we multiply the perturbed example x prime by the parameters omega, so we have that the result is the normal factor, which is omega transpose x0, plus a new factor representing the perturbation within my sample, within my image, within my data point. So what we want to do in this case is to maximize this new factor under the constraint that its norm in the FGSM approach, the norm is the max norm, is equal or lesser than this epsilon, this small epsilon. So the idea in this case is to set this perturbation equal to epsilon times the sine of omega. So why this is an interesting idea? So well, if we look at at what happens when we adopt this strategy, so we have that this omega transposed delta adversarial equal to epsilon times the sine of omega is equal to epsilon times the absolute value of omega 1 plus the absolute value of all the elements within the vector omega. So if we consider, for example, that m is the average of the absolute values of omega I, then we see that the influence of the perturbation grows as epsilon times n times m. So this is interesting because we are saying that the perturbation linearly grows with n. So even though we have a small epsilon, since we linearly grow with n, so this could be still a problem. So even though the initial perturbation that we added that we add to the data sample is very small, so if epsilon is very small, the final perturbation that we have in the result can be high. So this idea is then adopted, and so what the authors propose is to linearize the J, so our loss function, around the fixed value of the parameters, obtaining an optimal max norm constraint adversarial perturbation. So what they basically propose is to have that this delta adversarial is equal to omega times the sine of the gradient of our loss function. As for the other class of attacks, so untargeted and targeted attacks, so we basically have this definition, and in this case, it is easy to see that we can define the same problem in a constraint as a constraint optimization problem, or as an unconstrained optimization problem. So in the first case, we want to find the value of delta adversarial such that it minimizes the norm of delta adversarial, but under the constraint that my classifier applied to x0 plus the perturbation using some parameters is not equal to y0. So it is, or in the unconstrained version, it is equal to a new y, which is y prime. Analogously, we can define the targeted version of this attack, where in this case we have the constraint in the constraint variant of the formulation is such that the classifier classifies my sample, my perturbed sample, as y target, yt, which is y target, and the same is for the unconstrained version. So this is the formal way that we represent targeted and untargeted adversarial attacks. But we don't have only attacks, we also have countermeasures. So we also have defense strategies. And some of these defense strategies are, for example, adversarial training, defensive distillation, and robust optimization. And these are the proactive countermeasures, meaning that these countermeasures are applied before the attack. So we are just making our system more secure, more robust. Okay, this is the idea. On the other hand, we also have reactive countermeasure, meaning that we react only if we have an attack. So we want to find a solution to this attack. So this is the idea behind the defensive distillation proposed in 2017. So what we do here is to apply exactly the same approach that is applied in distillation. So we work on the softmax layer, where we have this our softmax function, and we have that within the softmax function we have this temperature term, which depending on its value, we have that the probability that a sample is classified as y is much more different from the probability of the other classes if t is quite small. So that's why usually t is set equal to 1. But we can have exactly the same result in terms of classification, but with a lower difference between the values that we have for the probability, if we set the value of t to a higher value. So with this distillation, just 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 a recap of distillation. So distillation has been originally proposed to deploy big models on small devices. So basically, we have what is called the teacher network and the student network. So what is done is that we train our huge teacher network on our servers, and what we do is that we do not consider just the labels as the result of my classification, but we consider all the values that we have for every single class, every single class that we have as the output of my classifier. And these values are used as labels for a smaller network that is trained on the same data. Okay, so the big network is trained trying to identify the correct label, but what we reuse within the student network are not the values are not the labels, but are the probabilities associated to every single label for every single sample. And in this case, so we can have a smaller network. In defensive distillation, the main idea is used, but in this case, we have exactly the same network. So the teacher and the student network are exactly the same network. So we have our initial network, which is trained. And once it has been completely trained, so we use the values associated to each class to train again the same network, but this time, as for classical distillation, we do not consider the labels, but we consider this probability values. Furthermore, in this case, we see that the network is the original network. Sorry, is trained with a value of temperature, with a value of T, which is between 40 and 50, and we see that with this value, the network which is retrained which is trained for the second time is more robust to attacks. So this distillation approach works for making the machine learning model more robust against attacks. So what is the definition at the end of this adversarial robustness? Well, the adversarial robustness is a min-max problem, where the idea is that, okay, we know that for an attack, we want to maximize the loss, and we want to find the value of delta adversarial such that this loss is maximized. But since we want to defend the system, so since we want to make it more robust, so we want to propose a defense strategy, so we want to find the value of our parameters for the model, so the omega values, such that the loss function is minimized. So this min-max formulation is used to capture the notion of security against adversarial attack. So this is what we call robust optimization. Adversarial training has been proposed as a technique for adversarial robustness by Goodfellow and Lee's co-authors within the same paper where they propose the FGSM attack. And actually, if we look at the formalism behind adversarial training, we see that the attack is somehow embedded within the formula itself. Here, the point is that we have this loss function where we add a regularization term containing the idea of the adversarial perturbation that we have already seen for the FGSM attack. Well, it is possible to show that by training the model by using this loss function, we increase the robustness of the model against the attacks. But very interestingly, we also show that this adversarial training provides better generalization performance. So what we have seen adversarial robustness is this game between an attacker and a defender. So we have an attack-defense game. And this is exactly the idea that we have behind the generative adversarial networks, so behind GANs. So in this case, the attack-defense game is a minimax game. In GAN, we have that the architecture is trained with an attacker that tries to alter the defender. So we will see that both the attacker in this case and the defender in this case are two deep neural networks that are part of the same architecture and that play this minimax game together. So GANs have been successfully adopted in many different application scenarios. So we have the very famous phase aging application that you maybe have used with your smartphone, but it has been used also for super resolution in images, for 3D object generation, starting from plain images, for image to image translation, text to image translation, and so on and so forth. So GAN have been used for many successfully for many generative approaches. So, but what is the idea? What is the architecture behind the GAN? So, in a normal classifier, we will call this classifier D, which stands for discriminator, as we will understand better in a while. We have that this classifier is able to understand if a picture belongs to a certain class with a very high probability. So the classifier says 1 or 0 if suppose that we have a binary classifier, if the image belongs to a class or not. So this is the normal behavior of a classifier. What happens with a GAN? So with a GAN, we have these two networks. We have the discriminator, which is exactly the classifier that we had before, and we have the generator. The generator tries to generate fake samples, and the discriminator needs to understand if the inputs that it gets are fake samples coming from the generator, or these samples are coming from real data. So in this case, what happens is that the generator maps a Gaussian random noise to fake data to fool the discriminator. So in this case, we have this output, which is GZ. And what happens to the discriminator is that it gets the output from the generator, GZ, and the real data. And starting from these inputs, the discriminator must be able to understand if the input is a real one or a fake one. Also, in this case, we can model everything as a min-max game. So we can model a J, we can model a function such that this function needs to be maximized with respect to the parameters of the discriminator, and at the same time, this function needs to be minimized with respect to the parameters of the generator. So in this case, what happens is that the generator generates something, the discriminator gets an input, and in this case, the discriminator is able to understand and to discriminate if the input is real or not. And the feedback, the feedback coming from this discrimination goes back to the generator. So if the discriminator is able to discriminate between a real or a generated sample, then this information goes back to the generator, and then the generator must improve its performance in generating better and better samples. So this is the idea. So if we consider dx as the probability of for the discriminator of identifying a real or a fake sample, then we can again model this this game between the generator and the discriminator as a min-max game. Because in this case, we have that given this J that you see in the slide, we want for the discriminator to maximize this function, which is actually, as we have just said, the probability that the discriminator is able to discriminate between the real and fake samples, while on the other side we have that the generator wants to minimize this this function. Then the final problem that we have is a min-max game, where we have this minimization of the minimization with respect to the parameters of the generator, and the maximization with respect to the parameters of the discriminator. So these are the very basic elements that you need to understand what will be explained in the next parts of this tutorial about GANs for recommender systems. So that's it for the first part of this tutorial. Now Yashar Deldjoo will tell you everything about adversarial learning, and with a particular focus on security of recommender systems.
Hello everyone, my name is Yashar Deldjoo. I'm the second one in this list. I'm an assistant professor at Polytechnic di Bari in Italy. And today I have the pleasure to be presenting the second part of our tutorial, basically focused on adversarial machine learning against recommender system models for your view. And I would like to thank Professor Tommaso di Noia for presenting the first part of this tutorial and foundation of basically adversarial machine learning, and other my colleagues which have helped me and helped our group to be presenting basically this tutorial this year at RecSys. So I want to start with going to the second part of this tutorial, which I'm responsible for. So I'm now following the slides. And basically, we are here at adversarial learning for security of recommender systems. Okay, so my lessons in collaborative filtering models, basically, or collaborative filtering model development over the past decades are depicted in this figure, as you can see. And as you can see with basically different colors, we can identify two major eras in developments of collaborative filtering models based on their main objective. The first era, which is focused on maximizing or enhancing the recommendation accuracy, and beyond accuracy is colored with green on the left. And the post-neural era, which is the transition era from classical learning to adversarial machine learning, is the one on the right. As for the accuracy maximization or optimization era, this is an era where the main effort of research community or the RecSys community, we can say, was concentrated on the golden objective of maximizing recommendation accuracy over years. Consequently, here machine learning models were developed that tend to use any available signal in the data to reach this goal, even though some of these data contain noise as a result of users' misoperations. So from an algorithmic point of view, we can classify all these methods on the left to classical collaborative filtering models plus side information, and modern algorithms such as deep neural networks and approaches based on graph learning. Nearly 3 decades of research on recommendation model resulted on a variety of models and metrics to assess their effectiveness. However, the eras on the right, which are colored with red or purple and yellow, are the focus of this tutorial. They showed the main application of adversarial machine learning plus RecSys, which are the one focused on security of recommender system, the part I'm responsible for. So this is the red or the purple part on the right upper part of this picture, and the one used in generative application, mainly generative adversarial networks, basically colored with yellow. So, basically, here in this figure, you can also see two main applications of adversarial learning, as I just said, which are characterized by the min-max game between a learner and the attacker, described in the first part by Professor Tommaso di Noia. So these are for the security of machine learning model, and second in GAN-based systems. Okay. Okay, so security of recommender systems has been studied in two main different contexts over years, or in the history of recommender system research, and we can call them the one related to handcrafted shielding attacks, which started from early 2000s and they're going on till now, but mostly they were studied by 2015, where adversarial machine learning did not emerge yet. There are a few works still published over the last year. One, our recent CFGAN paper by System Lab, which was published in the last year CFGAN conference as a full paper. And the other one is basically related to machine learning attacks, which is started from 2016, and it is an active research area now. A third and recently emerging area, which is the one in the middle, is also machine learn-based poisoning attacks, which I will talk about very briefly in the next slide. So in our recent book chapter, you can find example of research in this area, and here you can also see, for example, different type of research focus in each type of application. So, for example, for handcrafted shielding attacks, there have been work on leveraging the user interaction data or exploiting semantic data to craft better user profiles. And the work by our group, published at last year's CFGAN, it's a full paper which studies the impact of data characteristics on shielding attacks and basically detection and defense mechanism against shielding attacks. And the same you can find categorization of other research areas. So I would welcome everybody to take a look at our recent book chapter on Recommender System Handbook on example and research in these areas. So our main focus, or my main focus at least, would be on this, but I would give also a brief introduction about the previous parts in the next slide. So adversarial machine learning attacks is the main focus of this tutorial, but we're going to talk about the previous one shortly as well. Okay, so handcrafted shielding attacks, what are they? Let's start with their definitions. Okay, so given a user rating matrix on the left, as you can see, with n users and m items, the goal of a shielding attack or handcrafted shielding attack is to add a times n, so floor of this number, which a is a number much smaller than 1. So this value, the entire value a multiplied by n, is a fraction of users. The goal is to add this number of fake or malicious user profile, and with this constraint that each profile can have a maximum of certain number of ratings. Okay, so different attack types in basically RecSys or against these models are, for example, random attack, popular attack, bandwagon attack, and love-hate attack. So basically, these differ, or these are constructed based on the composition of the user profile, as it has been shown in the lower part of this picture. So the audience are invited to take a look at this review, Shielding Attack Against Recommender System, a comprehensive survey which was published at Artificial Intelligence Review in 2014 for further information. Okay, so the recent advances on handcrafted shielding attacks, basically we can name of the work by our research group named How Dataset Characteristics Affect the Robustness of Collaborative Filtering Recommendation Models, published in CFGAN 2020 as a full paper, which basically exploits an explanatory framework to study the impact of dataset characteristics, so user item rating matrix characteristic, and the robustness of these shielding attacks. Okay, so here are two take-home messages from this research. The first is that density and space have a negative impact on effectiveness of attack. What does that mean? It means that if you increase the density, or conversely, if you reduce the sparsity, the attack's effectiveness is reduced. So density brings robustness to the model. Okay, and this is something that has been proven somehow by this explanatory model. The second is that space has a positive impact, where a space here is the fraction of user over item. So having more user than items can generate a lack of robustness. So it is not a good idea to work to work with an user rating matrix that has much more user than items. So this may make them vulnerable to attacks. Other type of recent research directions on shielding attacks, or generally data poisoning attacks, are dedicated on proposal of novel defense strategies, for example, against user, the SVM classification method, and using user and item side information, as you can see here. As I said before, the readers are invited to take a look at this survey for established research area on this area, and also the recommender system handbook, which the second edition at least has a detailed section on handcrafted shielding attacks, especially for the years before 2014 and 15. Okay, now it comes with the second part, which is machine learned data poisoning attacks. So the previous handcrafted shielding attacks or data poisoning attacks are considered as classic attack types. So they have been exploited for many tasks, among others, including label modification, poison insertion, data modification, and boiling frogs. So I will explain some of these. So label modification, for example, is an attack in which the attacker basically alters some supervised learning labels within a certain overall budgets. Okay, hence there is a poisoning insertion attack in which the attacker can attach some new poison feature vectors with or without the corresponding target label. Whereas poison insertion here, the attacker can attach some of the poison feature vectors with or without the corresponding labels. And data modification is the one that the attacker can modify some of the existing feature vectors or labels in the original data before the model training. So the audience and the readers are invited to take a look at our recent handbook chapter on security of or adversarial machine learning attack and defenses for further information on these topics. So the main limitation of these, let's say, these classical poisoning attacks is that they are empirical. They use empirical techniques and are based upon heuristic approaches, and they do not provide a specific optimization procedure to maximize the adversary's goal. So this section we're going to talk about, it talks about a specific type of data poisoning attacks against recommender system that provide a specific optimization procedure to maximize the adversary's goal automatically. Okay, so we come to the central question, which is mentioned here, and that is which kind of attacker utilities we can maximize, or the attacker can maximize. So Chen et al. In this following paper, which you can see here, data poisoning attacks on cross-domain recommender system, talk about three types of attacks. They're called availability attack, integrity attack, and hybrid attacks. So in availability attack, the attacker tries to maximize the estimated error in the target domain, whereas in the integrity attack, the attacker's goal is to increase or decrease the popularity of a subset of items. Okay, and hybrid attacks are a mixture of the above attack types. So the next relevant question is which recommendation models could be optimized. Okay, so here we should point out that data poisoning optimization is generally different than classic optimization. for recommendation utility. And basically, for data poisoning optimization attacks, we need to have these three types of information at hand. First, the target recommendation model. Second, an attacker utility. And third, an optimization procedure for that utility. And to answer the above question, we can say that in principle, every model could be optimized for data poisoning attacks. However, in the literature, we find basically research focus on the following type of models or recommendation models, which are factorization-based models, reinforcement learning-based models, graph-based model, and the one based on memory-based k-nearest models. And these are ordered in the decreasing order of popularity, and basically we can mention a few words, for example, about the first two for your interest. So in poisoning factorization-based model, the attacker utilities or strategies in the literature are as following. First, the type of attack used are mostly focused on availability, integrity, and heart attack, which are the three types of attacks. So all these attack types are used. Usually, the focus is on hit ratio maximization, which is a metric to evaluate attack success. And they use tests like Wilkinson test in order to check the quality of these attacks. And some of these works, some of the research area in this topic explores a subset of influential users to modify top-end recommendations. Defensive strategies, however, for example, in the general case of data poisoning attacks or machine learned data poisoning attacks, use SVM classifier to detect fake profiles trained on specific features or indicators. Okay, and here are the examples. And team learning to conduct a clean learning for the recommendation model, and robustness analyzer to certify that a factorization model is robust. And regarding reinforcement learning models, the information needed to conduct these type of attacks is more, and they include the following. So we need to define the recommendation model in hand or a proxy thereof, the attacker knowledge and capability, which is common to other attack families as well, the attack space and the state space and the action space, which is the first case is a sequence of actions or an embedding, and the second case is the items that can be chosen or an embedding. And finally, the reward utility. Okay, now we can talk about adversarial attack and defenses against recommender systems. Okay, so unlike images, there are considerable differences or challenges in adversarial attacks on recommender system compared with classical attacks. And you can see here some of the challenges of adversarial machine learning attacks against recommender system models. What are they? First, adversarial examples created for example, image classification attacks are empowered based on continuous real-valued nature of these data, which are the pixel data. But in recommender system, the raw values are user or item IDs and ratings, which are all discrete or binary. Perturbing these discrete entities is infeasible, since it may lead to changing the semantics of the input. For example, loosely speaking, if you add some noise to an ID, it can result in a new user ID. Okay? Therefore, existing adversarial attacks which were conducted against continuous rating features are not easily applicable to recommendation models. So these methods like gradient-based approaches, FGSM, BIM, PGD, CNW are not suited for to be used against recommendation models in an off-the-shelf manner. Number two, in images, we have this notion of unnoticeable, where the attacker aims to attack an image in ways that it remains unnoticeable. How can we model the notion of unnoticeable in binary and discrete recommender system? Okay, So most popular approaches for adversarial attacks have generated them by adding perturbation on embedding or model parameters of recommender system. Okay, their main goal has been to study the stability of training when minimal alteration of parameters is applied. Okay, but generally this remains as an open research question. Okay. So, as it could be seen in the last part of this table, adversarial attacks on recommender system have been studied in three main research areas: adversarial perturbation of model parameters, adversarial perturbation of content data, defense, and robustification. Let's start by talking about the first, adversarial perturbation of model parameters. Okay, so from a general perspective, just like adversarial machine learning against classification systems, the goal here is to add or is to apply additive perturbations on model parameters of recommendation like BPR, considering two perspectives: the attacker perspective, which wants to reduce the accuracy of recommendation, and the defender perspective, which wants to study the robustness or stability of training by adding these perturbations on the model parameters. Okay, as an example of this research area, we can focus to the work by Xiangnan He on CGAR 2018 called Adversarial Personal Ranking for Recommendation, where they showed that by exposing basically the model parameters of BPR to adversarial perturbation versus random perturbation, the NDCG, the test NDCG of the recommendation decreases from -21 to -1%. And this is a difference of 13 times difference, showing the impact of adversarial or perturbation generated by an attack model as opposed to just random perturbations. Okay? And another recently popularizing research area is adversarial machine learning RecSys against multimedia recommender system. Okay, so here's another example work by a research group in which the Noia et al. Studied the simulation of targeted adversarial attack against multimedia recommender system, in particular a fashion recommender system. And they showed that by perturbing product images in a human unnoticeable manner, they can push low recommended product categories 3 times more recommended. Okay? And finally, we talk about the defensive approaches against adversarial samples or adversarial examples. So from a broad perspective, the defensive mechanisms against adversarial attacks can be proactive or reactive. Okay? And they can be classified as basically robust optimization methods or detection methods. Okay, but here we are talking about approaches that make the recommender system models robust. So they are called robust optimization method and the one based on defensive distillation. So speaking about robust optimization, so at the heart of this method is to formulate models that can correctly classify both adversarial and clean samples. So robust optimization, which is nothing but the Minimax game presented in the previous part of these slides, this tutorial, is basically equivalent to robust optimization in the context of adversarial perturbation or adversarial attacks. Okay, and different approaches of robust optimization we can name of. So these are different approaches to solve less optimization methods, which are adversarial regularization, robust gradient descent, and certified robustness. And in the literature recommender system, the first one has been the most popular, or we can say the only approaches used so far. So we're going to talk about that particular method and leave the rest for audience interests. The readers or the audience are invited to take a look at this very interesting book on adversarial machine learning published in 2018. as synthesis lectures on artificial intelligence and machine learning. So let's talk about adversarial regularization or adversarial training directly in the context of recommendation. So this figure shows a notional view of adversarial recommendation. So integrating the adversarial perturbation on user items and their side information, basically model parameters. It is important to note that while in computer vision domain, these perturbations are added on raw data, for example, pixel values in recommender system, they're applied on model parameters of a recommendation strategy. Okay, as you can see in these figures. So in particular, adversarial perturbation against recommendation models are applied either to directly user profiles or embeddings of those, and basically embeddings or model parameters of user side information and item side information. So once again, the adversarial noises, adversarial perturbation are added on model parameters of basically user and ratings or their side information, okay, as you can see in these figures. So from attacker perspective, the attacker's objective is to maximize the recommendation prediction loss by adding a minimal amount of perturbation according to a certain norm type. For example, norm 2, norm 0, or norm infinity. And epsilon here is called the perturbation budget, which is typically chosen as a small value. And for example, FGSM, which was described in the previous part, has the objective to use a first order approximation of the loss function and uses the sign of the gradient function to construct adversarial samples for the adversary's target loss. Okay? Now let's talk about the defensive approach, adversarial training as a defensive strategy. So what is the goal? Basically, adversarial training is a data augmentation training process where one tries at each update to approximately solve the inner attack problem in the Minimax game. Okay, and generate adversarial examples according to its inner attack problem, and then feeds them into the training data to provide harder examples for the defender. So this is how the system works. Furthermore, the defender, this model, uses the worst case loss function here as a regularization component, as you can see in the right side of this slide, to explicitly trade off between two components. It is robustness on adversarial samples and accuracy on clean data. Okay, so against this result, so this results in a min-max formulation to capture the notion of security against adversarial attacks in the principal approach. So the inner maximization is the definition of adversarial attack, which we presented in part 1 of this tutorial, and it aims to find perturbation delta that maximizes the prediction loss of the model, and the outer minimization that aims to find model parameters that minimize adversarial loss produced by the inner attack problem, or more precisely, robust optimization using adversarial training. So here's a summary of how adversarial training works for a recommender system. Given training data, X, and the parameter epsilon, lambda, and alpha, and we first use the pre-trained recommendation model and do this while loop until certain stopping criteria is satisfied. Randomly select X or a mini batch from the training data, construct adversarial perturbation according to certain attack types, and update model parameters according to the model to adversarial learning model framework. Okay, and do this iteration until certain criteria is achieved. So here's an example of a very interesting paper by Zheng and He in 2018 in their CIGAR-R papers, where they show the impact of adversarial perturbation on embedding vectors of user and item according to the equation you can see in this figure. So here's a snapshot of the result. Let's analyze what does it mean. On a 3 given data set, for example, on Guala, we can see the impact of adversarial attack with different logics. And for example, we can see that the test NDCG reduction goes from -26 to -78% when we go from lower perturbation to higher perturbation. And these show the impact of adversarial perturbation on reduction of a test accuracy against common recommender system models. And here we can again see the difference on impact of adversarial noise versus random noise, as we briefly mentioned before. For example, we can note that the target evaluation metric here decreases by increasing the perturbation budget both in train and test data. Okay. One main explanation for these behaviors of adversarial perturbation is that adversarial perturbation uses or exploits all the imperfection or the imperfections and approximation made by the machine learned model during the training phase to control the model's outcome in an engineered way. Okay, and in that way, it can more successfully decrease the text quality. And as we said, to protect models against adversarial attacks, adversarial training was applied, or adversarial regularization. And we mentioned that adversarial regulation or adversarial training is a defensive mechanism whose goal is not to detect, rather build models that perform equally well with adversarial and clean samples. So adversarial training consists of injecting adversarial samples generated via a specific attack model such as FGSM that basically not only provides, that is able to provide robustness against noisy sample and better generalization performance on clean samples. Okay, and here is a snapshot of results against by using adversarial training. We can see, for example, on Guala dataset that by using APR, the quality of how much the quality of or the decreased quality of basically models against adversarial attack is returned. For example, for epsilon equal half, you can see against adversarial attack, the reduction was -26%, and now it's -2.9%. And when this goes to epsilon equals 2, it's -78% versus -29%. Okay, so this shows how much adversarial training is basically impactful on returning these return results. So generally speaking, these results highlight the failure of classical machine learning models in adversarial settings. And they advocate the importance of adversarial machine learning as a new paradigm of learning to design more secure models. Okay? And finally, here we can see the improvement on general recommendation performance or generalization, which basically compared to different recommendation models, you can see the improvement goes from 3% to 400% depending on the model used. So AMF, the last one, is the model equipped with adversarial training defensive procedure. And as we saw before, it not only improves the robustness against adversarial attacks, it further increases the general recommendation performance on clean samples. Okay? And basically, these results highlight that adversarial learning or the power of adversarial learning in both of these scenarios. So here is the more focused or zoomed, let's say, part of the results. And finally, we can point out the reader to a similar application of adversarial machine learning for multimedia recommender system, and we point out the audience to the work by Xiangnan He again on their transaction TKDE19, where this time they add adversarial perturbation on model parameters of item side information, in this case, images. And so basically adversarial perturbation are added here on the third category, which is the content embedding. So in particular, user item content embedding. Again, we can see the reduction of the impact of applying adversarial perturbation, which, for example, on if you look at epsilon equals to 0.2, which is a very, very small number, we can see the impact is minus 67% for Amazon dataset and minus 31% for Pinterest. So this shows the powerfulness of adversarial perturbation against content data. Okay, and by applying the defensive adversarial training, we can see that, for example, on epsilon 0.2, from minus 67, we can go back to minus 20%, and from minus 31%, we can go back to minus 18%. And this again shows how much classical machine learning models is fragile against or insecure, basically, against adversarial attacks. Okay. And again, we can see the generalizing or the relative improvement of recommendation model using adversarial training, which in this case, you can see the improvement goes from 5% to 52%, depending on the recommendation models, when the recommendation model of BPR is equipped with adversarial training procedure. Okay. Finally, we would like to point out two other interesting areas that are currently going on, which are, for example, attack and defense on deep neural models or autoencoders, attack and defense on factorization machines, adversarial regularization to improve sequential recommendation, and perturbing user continuous input, and attack with CW or defense against using defensive installation, which are more niche type of domains, type of applications or attacks studied by the RecSys community. And here is a very short snapshot of different domains, and these attacks have been conducted on. There have been 35% adversarial machine learning used in social media dataset, 50% on media dataset like music and videos, and 14% on products. Again, we would invite the audience to study our recent publications, basically on adversarial machine learning in recommender system, which is a survey have been accepted with a minor review at ACM Computing Survey, and an extended version of basically written on the book chapter of recommender system titled Adversarial Recommender System Attack, Defense, and Advances. We hope, currently there is an archive version of the survey available online, and we hope we will be able to provide at least a preprint of the handbook chapter by the end of this year. So on behalf of my group, I would like to thank the audience for listening to the second part of our tutorial, and I would like to invite you to follow this tutorial for the third part on generative adversarial network and the practical hands-on session, which would be presented by my colleagues. Thank you very much, and have a nice day all.
In the previous parts, we focused on the class of discriminative models, where the main aim is to learn a conditional probability given an input. We will now focus on a novel class of generative models, named Generative Adversarial Networks, GANs. A generative model takes care of the generative process behind data to categorize the data instances. In adversarial learning, the generative models can be particularly helpful because they generalize well and learn unknown user preference distributions. These aspects let us model user preference in complex settings. This kind of model has been widely exploited in the recommender system research for improving collaborative recommendation, context-aware, domain transfer, cross-domain recommendation, security, and fashion recommendation. Before examining the literature in detail, I need to introduce you on how we can produce recommendation leveraging GANs. To this extent, I will depict a general framework that unveils the key features of GAN-based recommendation. We can undoubtedly start from two pioneering works, IRGAN and GraphGAN, proposed in 2017 and 2018. IRGAN proposed to and formulated how to exploit GANs in three different information retrieval scenarios. The classic query-based retrieval task, the recommendation task, and the question-answering task. On the other hand, GraphGAN focused on graph representation learning and proposed how to improve learning by exploiting GANs. To unroll the details of the model, we can start from IRGAN. The rationale is that we can assume that there is an unknown stochastic generative model that binds items and users, such that, given a user, we can obtain an item. In particular, the generative model's goal is to generate items relevant to the given user. Then, we can assume an unknown relation between users and items that could let us know the estimated rating of an item, given the item and the user. Indeed, the discriminator goal is to distinguish whether, for a user-item pair, this relation holds or not. GANs were deep generative models originally proposed by Goodfellow in 2013. A GAN is composed of two components, a generator G and a discriminator D. The generator works to capture the real data distribution to generate adversarial examples and fool the discriminator, while the discriminator tries to distinguish the fake examples from the real one. This competition, known as adversarial learning, ends when the components reach the Nash equilibrium. In the figure, we can see how GANs can cope with the recommendation task by conditioning the generator with the user information. For recommendation, we use a particular kind of GANs, the conditional GAN. Conditional GAN extends the conventional GAN by incorporating an extra condition information term on both the input of the generator G and the discriminator D and conditioning them. The dependence from the user is reflected in the loss function through a conditional probability. Here, the generator is conditioned by the user information to make the network produce tailored recommendations. At the same time, we can see another conditional probability in the first term, that denotes that also the discriminator is conditioned by the user. If we analyze the cost function closer, we can note that the discriminative network wants to find the best model parameters phi to discriminate true user item rating prediction from the others. On the other hand, the generator goal is to produce better user item pairs, thus minimizing the overall error. These opposite optimizations compose a minimax game in which the goal is to find the best parameters theta for the generator that minimize the loss, and find the best parameter phi that maximize the loss. Now we can update the picture, highlighting the optimization goals for the generator and the discriminator. We can also analyze the training by adopting another perspective. While the discriminator tries to separate observed samples from the others, the generator tries to generate, or better select, the best user item pairs that could be put in the observed samples space partition. Now we can draft an optimization algorithm. First, we initialize and pre-train the generator and the discriminator. Then we start an iterative procedure in which G generates K relevant items. The relevant items are combined with the real items and analyzed by the discriminator. And the loss is sent back into the network to update the parameters. Unfortunately, in the recommendation scenario, we deal with discrete IDs of items. Consequently, the gradients of the loss cannot be directly applicable to the GAN. To solve this issue, we need a differentiable item sampling procedure. In the literature, this problem is usually solved with the adoption of a differentiable sampling strategy. The first approach is to rely on an algorithm that comes from the reinforcement learning research, the policy gradient-based reinforce algorithm. The second approach is to define a specific differentiable loss for sampling by adopting the Gumbel-Softmax loss. The reinforce algorithm is designed to derive the objective function for policy gradients directly. In practical terms, the goal is to learn a policy that maximizes the cumulative future rewards. Reinforce is a Monte Carlo variant of policy gradients in which we take random samples. The agent collects one episode trajectory using its current policy and uses it to update a policy parameter. However, as the number of items increases, the reinforce has shown to be unstable. To solve the issue, we can use a reparameterization trick, refactoring the sampling of items into a deterministic function with the fixed distribution. The factoring of the sampling process does not make it differentiable. Since the non-differentiability comes from the argmax function, we can easily perform backpropagation once we have a differentiable approximation of argmax. When we approximate argmax with this exponential formula, we sample from a specific distribution, which is the Gumbel-Softmax distribution. Once these foundations are clear, we can easily face the different application of GANs in the recommendation scenario. There are several examples of the application of GANs in recommendation. If we want to make a coarse categorization of these approaches, we can divide it based on the recommendation strategy and the recommendation task. Today, we will try to cover the collaborative, contextual, cross-domain, and complementary recommendation, despite the little time available. CFGAN has been introduced to address a problem with discrete items in GAN, where G produces a single item index at each iteration, which is a discrete entity in nature. This is different from the original GAN in the computer vision domain, in which the output of G is an image, or better, a vector. The generation of discrete item indices by G results in poor sampling of items from the pool of available alternatives by producing samples that are identical to the ground truth. This deteriorates the performance of G and D during the min-max training iteration. CFGAN introduces vector-wise training in which G generates continuous valued vectors to avoid misleading D, which in turn improves the performance of both G and D. In these figures, we note the degradation of the discriminator's performance on the left and the different behavior of the vector-wise implementation on the right. Instead, in these tables, the authors showed improvement of CFGAN over GAN and GAN baselines. Wang et al. Propose GAN, a graph-based representation learning that leverages network embedding for collaborative filtering and recommendation. The graph-based analysis is gaining momentum in recent years due to the ubiquity in real-world problems, such as modeling user preferences for item recommendation, as well as social graphs and social media networks. Co-occurrence graphs in linguistics, citation graphs in research, knowledge graphs. GAN further proposes the Gumbel-Softmax instead of traditional softmax, which appears to boost the generator's training computational efficiency for graph sampling and embedding learning. The central idea of network embedding is to represent each entity in a graph with lower dimensional latent representation to facilitate tasks within the network and prediction of entities. For example, such latent representation makes it possible to perform prediction for supervised tasks, while the distance between nodes embedding vectors can serve as a useful measure in unsupervised tasks. GAN can be viewed as graph-based representation of GAN, where queries and items are nodes of the graph. For a given node, the generator's objective is to learn the ground truth connectivity distribution of the vertices, whereas discriminator aims to discern whether or not a connection should reside between vertex pairs. The next work focuses on inactive users. The core idea of OCF is to generate sufficient real interaction data for the inactive users with the help of side information and GANs. And then a pure collaborative filtering method could be performed on these augmented dataset effectively. However, the authors face three major challenges to implement this idea. First, how to ensure the correctness of the generated interaction data. Second, how to combine the data augmentation process and the recommendation process into a unified model and train the model end-to-end. And third, how to make the solution generalizable for various side information and recommendations tasks. To train OCF, the authors utilize a two-phase procedure. Phase 1 aims to obtain a good data augmenter, where the generator and the discriminator play a minimax game and eventually reach an equilibrium, where the generator generates a tuple that the discriminator can hardly discriminate. Then, in phase 2, the generator's parameters are fixed and it only acts as a data augmenter, while the discriminator is trained to correctly map a user item pair to a ground truth label based on data from both the original dataset and the well-trained generator. The generator aims to obtain a fake but plausible interaction record. First, they sample a user U based on a subsampling strategy with the frequency of user U, or better, the number of use interactions, and a predefined threshold. By exploiting the activeness of users, the authors ensure that the less active users have higher probabilities of being sampled. The authors test OCF with two different hybrid settings. Content-based OCF exploits textual context to tackle sparsity. Here, the generator is a state-of-the-art content-based recommendation method, DeepConN, which models users and items jointly using the textual reviews. Specifically, it learns hidden latent features for users and items based on convolutional neural networks. The second setting is named sparse feature-based OCF. The side information in some datasets presents in very sparse formats. These almost all of the elements of a training vector are zero, which usually results from dealing with large categorical variable domains. One of the most effective neural network-based solutions to address this challenge is the wide and deep learning framework that the authors use as the generator. It jointly trains wide linear models and deep neural networks to combine the benefits of them for recommended systems, where wide linear models can effectively memorize sparse feature interactions using cross-product feature transformations, while deep neural networks can generalize to previously unseen features interaction through low-dimensional embeddings. The next work deals with contextual recommendation. Indeed, Plastic tries to integrate the long and short-term information by means of a recurrent neural network while generating recommendation lists that can achieve a higher cumulative rewards. Plastic adopts matrix factorization and LSTM cells into the generator to account for the varying aspects of both users and items, while a two-input Siamese network is built manually using a matrix factorization and a recurrent neural network as discriminator that encodes both the long-term and session-based information in the pairwise scenario. Another relevant application of contextual information is the point of interest recommendation. In this field, many approaches have been proposed over the years, especially after the mobile revolution. GeoILM is a GAN-based POI recommender that integrates the geographical features with a GAN to achieve better POI recommendation. In the proposed system, G improves the random negative sampling approach and pairwise POI recommendation scenario that leads to a better representation of users and items and enhances recommendation quality with respect to state-of-the-art models. The particular feature of this approach is to use the generator to improve the generation of negative samples by exploiting the reinforced algorithm. Moreover, within the generator and the discriminator, we can find specific geographical constraints that take into account the nearest POIs and regions. Inspired by the efficacy of adversarial negative sampling techniques proposed in GeoILM, another work addresses the limitation of typical negative sampling in the social recommendation domain in transferring user information from social domain to item domain. The deep adversarial social recommendation system exploits adversarial learning's power to dynamically generate difficult negative samples from user item and user-user pairs to guide the network to learn better user and item representations. The system is composed of three key elements: a cyclic user modeling and two distinct adversarial learning procedures designed for the two different domains. The cyclic user modeling is in charge of transferring the user information between the social domain and the item domain. The user representation itself serves as a bridge between the two different domains. As we have observed with GeoILM, the generator can be used to generate better negative samples. Here, this generation is conditioned by the user representation and thus by the information that comes from the social domain. In an analogous way, the adversarial learning that takes place in the social domain will be conditioned by the information that comes from the item domain. Once the training procedure terminates, when we use the generator, we obtain two representations conditioned by the user. In other words, we obtain two embeddings that can be used for recommendation purposes. The authors validate the effectiveness of the system comparing with the state-of-art pairwise ranking and GAN-based models. As we may observe, deep adversarial social recommendation outperforms both. Craft addresses the problem of recommended complementary fashion items. The approach uses visual features by exploiting an adversarial process that resembles GAN and uses a conditional feature transformer. The generator acts like a feature transformer that for a given query product image maps the source feature into a complementary target feature by playing a minimax game with the discriminator with the aim of classifying fake and real features. For training, the system relies on learning the co-occurrence of item pairs in real images. In summary, the craft does not generate new images. Instead, it learns how to generate features on the complementary fashion items conditioned on the query item. These features are then used to recommend new items. In figure, we can observe as craft behaves definitely better than other techniques. The green boxes are the recommendation considered as acceptable by a fashion specialist. The next work tackles the complementary fashion item recommendation task from a completely different perspective. Indeed, CFGAN is a conditional generative adversarial model that draws realistic samples from paired fashion clothing distribution and retrieve real samples to pair with arbitrary fashion pieces. In practical terms, given an image of a shirt, CFGAN draws realistic samples from a parameterized conditional distribution learned as a conditional generative adversarial network to generate the pants that can go with the shirt. The classic GAN generator is modified to integrate three different losses. The mean square error to impose the new image to be mathematically similar to the original one. The perceptual loss that guarantees the similarity of the images after the application of several transformation filters, and adversarial loss that promotes the generation of more natural images. Here, we can observe on top the image query and the ground truth. In the left box, we have a classic image retrieval output, and on the right, the better complementary recommendations that are realized by CFGAN. The last work of this part is Adversarial Attacks on an Oblivious Recommender. That has been proposed in last year's edition of RecSys. This work is completely different from the previous ones, since the generator's goal is to generate adversarial user profiles to degrade the top key recommendation quality. Moreover, they make the adversarial user profiles unnoticeable by preserving the proximity of the real user rating interaction distribution to the adversarial fake user distribution. Finally, since the adversary does not have access to the gradient of the recommended objective, the authors derived an algorithm built on the zero-order optimization approach. In detail, to make the fake user profiles unnoticeable, the authors transformed the one-dimensional user profile vector to a two-dimensional vector to exploit the DC-GAN architecture. Although there are several other one-dimensional convolutional techniques that could behave better, the training of the generator on the right shows that the method effectively minimizes the Jensen-Shannon divergence. To sum up, we have explored together several applications of GANs to recommended systems. In fact, given the limited time, we have seen only a representative fraction of the works that have been proposed. However, if we adopt a broader view, we can also note that for the generator architecture, there is a prominence of linear models and neural networks. Among the artificial neural networks, the more represented classes are autoencoders and variational autoencoders. Moreover, if we move to a recommendation task-oriented perspective, we can observe, as expected, the prevalence of recurrent neural networks for the temporal-aware recommendation and prevalence of convolutional neural networks for the complementary recommendation. Although the high interest that is growing up on adversarial learning, several challenges and open research directions still remain. First of all, the majority of works focused on movie recommendation, leaving all the other domains almost uncovered. Since the recommendation task poses several domain-specific challenges, it would be interesting to witness how adversarial learning can tackle these challenges. Finally, beyond these problems, there are several domain-agnostic research challenges that are still open. So far, we've explored two main approaches for the non-differentiability of discrete item sampling. Are there other possible alternatives out there? More, the complementary recommendation has been focused almost uniquely on items. How could we integrate the user personalization in this process? Now, we have seen that some GANs can deal with some content or site information. Now, is that possible to further extend these approaches to deal with more structured information and knowledge-aware recommender systems. Moreover, even when the GANs are used for the attacks, it is really rare to observe another deep neural network-based model as the victim. And finally, as we have observed today, most works show the improvements obtained with GANs on classic recommender systems datasets. However, it will be interesting to observe the performance of these methods with real users in a completely online evaluation setting.
Good morning or good evening. I am Felice Antoromerra, a second-year PhD student at the Polytechnic University of Bari. During this part of the tutorial, I will present you the hands-on session of the tutorial related to the adversarial training or regularization of a recommender system. Basically, the main field of study of the adversarial learning is the study of the security of models, machine learning models, and in our case, recommender system. The main aspect of this branch of study is that after the definition of an adversary treat model with its goal, knowledge, and capabilities, we have also to defend and protect our model with a defense procedure. And in this part of the tutorial, we will practice with a real attack and a real defense to verify how much we are able to decrease the model performance and also to protect the model from the adversary treat model that we are going to define. Before we dive into the practical aspects, it is important to contextualize this hands-on session. In this case, in fact, we are going to analyze one of the most important and spread application of adversarial learning, which consists in the addition of adversarial minimal perturbation on the learned model parameters in order to study the robustness of recommender system. We have seen that we can perturb the model parameters with respect to user item matrix and its embedding version, but also for the side information related to the users, such as reviews or tags, but also items, such as the content. In this section, we will start from running a Jupyter notebook. This page that you can see in this slide will be available during the 2 live presentation, which will be duplicated. After you click on this widget builder, you need some minutes since it will build a cloud machine to allow you to run the code and experiment without installing any type of environment. Everything is executable via your browser. And the first page that you have is the Jupyter main notebook. In the top of this Jupyter notebook, we can see the outline of the exercise that we are going to apply. Firstly, we will train a classical baseline model-based recommender system, which is the BPRMF, on a small section of movie length 1M for temporal limits. Then, after the evaluation of the performance, we will define an adversary treat model. We will apply the attack and verify the decrease of performance. Then we will be ready to apply the adversarial training procedure to protect the model and evaluate how much we are able to improve the robustness. Let's start with the exercise. The model that we are going to analyze is a latent-based model, and it is BPRMF. The main idea is to decompose the user rating item matrix into two small matrices, one for the users and one for the items, with a latent dimension D, which is smaller than the number of users and the number of items. Here it is important to clarify that we are presenting the P as the matrix for the users and Q the matrix for the items. And it is the first part of the tutorial. We need to define our model. In this init section, which is the constructor of the model, we will use some predefined parameters like the embedding size, the learning rate, a coefficient of regularization, the number of epochs, the batch size, and some other information that are useful. But it is also important to analyze that we are going to initialize the model parameters, which are the P and Q that we have seen before. After the definition of the model, we can train the model for the number of epochs that we have specified in this classical train loop. And here we have also the training step with respect to the batch of user item interaction from which we are learning during that iteration. And here self point loss OPT is the loss function that we are going to optimize to learn the model parameters. At the end of the training of the clean model, which will be applied with the recommender model.train method, we will evaluate three very common metrics, which are the iteration at K, the normalized discounted cumulative gain at K, and the area under the curve. After the evaluation, we can and we will run the attack. The goal of the attacker is to break the model. Break the model means to decrease the performance. And the model of attacks that we are using, the method, is the fast gradient sign method proposed by Goodfellow in computer vision and readapted by he in the case of recommender system. In this slide, we have the epsilon, which is the budget perturbation, and delta, which is the size of the perturbation. And these formulas are then applied in our code. In fact, in the function execute adversarial attacks, we can pass and define the epsilon, so it is the size of the perturbation. Increasing epsilon, we will expect to decrease, to have a more important decrease of the recommendation performance. And as you can see, the evaluation of the perturbation is with respect to the model. We evaluate the loss function of the model, we evaluate the gradient, and we evaluate the normalization, the L2 normalization of the gradient to build the delta P and delta Q, which are the adversarial perturbation applied for the user embeddings and item embeddings matrices. And we have here the epsilon. It is used to limit the perturbation inside this boundary. And after the execution of the attacks, where we have specified the budget, we will evaluate and verify how much the performance of the model has been reduced. And here we have to defend the model. To defend the model, we will use the adversarial regularization or adversarial training procedure, where the basic idea is to minimize the object function with an adversarial regularization component that is the adversary treat model. So, knowing that we are perturbing with respect to this formula, we need to defend by minimizing that attack. And here you can clearly see the Minimax game, which is at the core of many applications of adversarial learning. And one of these applications are the generative adversarial network. This Minimax game is at the core of that application of the adversarial learning. And here we have again the Minimax game, but what it is interesting is to analyze how we have implemented this part. Again, the implementation is based on the inference with respect to the positive and negative k-pairs with user positive item, user negative item, which is classical in Bayesian personalized ranking. But then we need to evaluate the attack and the adversarial regularizer. After we have built adversarial regularizer in this part of the code, we can have the new loss function, which has been defined before, where we have the main loss component and the adversarial regularization one, which is this last line of code, where the adversarial matrix factorization loss function, it is the name of the model given by E in his work, is composed by the classical BPRMF loss function and the adversarial regularizer component, where the adversarial regularizer is the product between the adversarial regularization term that we have evaluated with the application of the attack on the model multiplied by the regularization factor, the coefficient lambda. And after the adversarial training of the model to protect the model, will we again evaluate the model and verify if we have improved the performance under attack. So it means that if before we add a decrease of performance by 20%, in this case, with the defense under the same type of attack, in this case, an attack with epsilon 0.5 and the attack method, the fast gradient sign method, we will have protected the model if and only if the decrease of the performance is lesser than the one before. So at the beginning, we can have 20% and then 5%. It means that the defense model is working in this specific adversary threat model. It doesn't mean that the adversarial training procedure with epsilon equals 0.5 will work with other attack models. And it is somehow important to have this type of clarification when we are going to protect with respect a specific attack model. So this is what we are going to explore and experiment during the Ensign session, and we will be very happy to have you during this section on the night between the 25th and 26th, and the morning of the 26th in the Central Europe time. These are some hours of the two session A and B. Thank you very much for your attention.